Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our third set of notes from Chapter 10, dealing with kinetic molecular theory and other ideas. Now, the basics of molecular motion for gases are described by what's known as kinetic molecular theory. It's how the motions of the particles affect the behavior of the gas particles. And there's like 6 different tenets that we're going to look at. So one, gases consist of large numbers of molecules that are in continuous random motion. So particles of solids, liquids, and gases, none of them stop. They're in continuous random motion until they collide with something, then they'll bounce off. The combined volume of the molecules of the gas is negligible relative to the total volume in which the gases contain. So fundamentally, the volume of the gas is not determined by the volume of the individual particles summed up, because those are so incredibly small compared to the overall volume. We would consider that individual volume of the particles to be negligible, and the volume of the container is the relevant volume in gas situations. Because solids and liquids are closer together and have attractive forces that hold them closer together, that assumption is no longer valid when we're dealing with solids and liquids, but it would be true of the gas. Independently, these molecules, regardless of their actual size, we treat them if they're these tiny little dimensionless points that are filling the volume of the container. There's no attractive or repulsive forces between the gas molecules. And the way we say that really is that they're negligible, which is saying that they're so small at the speeds they're moving, they might as well be zero. And remember, that's important with gas behaviors, is while there are attractive and repulsive forces that can exist between the particles, because of the relative speeds of these particles, relatively high compared to solids and liquids, and the distance apart, and remember, distance kills attractive forces through Coulomb's law, these particles are considered to have no intermolecular forces in their gas, yes, in their gaseous state. Fourth assumption of kinetic molecular theory as it applies to gases is that energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time as long as the temperature is constant. So in a room at constant temperature, while some particles collide with other particles, one speeds up, one slows down, so to speak, through all of those collisions, the net amount of kinetic energy is constant. So the average kinetic energy doesn't change. Individual kinetic energies do vary. Now, what you're looking at here is an important type of graph. It's known as the Maxwell-Boltzmann distribution. It's something we've talked about in first year chemistry, this style of graph. We just probably didn't give it its formal name. But it's a core idea here when we're looking at kinetic energies. The height, or I should say what you've got on this is molecular speed versus the fraction of the particles at those different speeds. And you can see we have relatively few slow-moving particles, relatively few fast-moving particles, and then the rest of the particles are somewhere in between. Now, one of the common misconceptions when students look at this graph is they think the blue graph is the higher temperature situation simply because it's larger. The blue graph would actually represent an average speed of particles, probably somewhere around here. And if you compare that to the red situation, which is going to have an average somewhere in this area, probably a little bit to the left of what I just drew, but you can clearly see the red one has a higher average speed. That must mean it's at a higher temperature. So temperature, average kinetic energy, and the speeds of the particles are all proportional and related to each other. So don't be fooled. The taller blue graph is actually the colder temperature situation. And the area under each of these curves is the same, 100%. So in order to increase the temperature and flatten out the hill, basically the hill's got to get smaller and shifted farther to the right. So this is a typical graph that we would use called the Maxwell-Boltzmann distribution. And it looks at the average kinetic energies, which would be related to the molecular speed versus the number of particles at that speed. Fifth would be the average kinetic energy of the molecules is proportional to the absolute temperature, which is just what I mentioned a second ago. The higher the temperature, the higher the average velocity of the particles, which would mean the higher the average kinetic energy. And once again, remember the red situation is the higher temperature, higher average kinetic energy situation. Now, the U that you see on each of these two graphs is actually what's known as the root mean square speed, the RMS speed. And that's something that we don't really get into. It is talked about in the textbook. It's basically the speed of a particle at average kinetic energy, but that's not something that you need to know for a test or the AP test. Now, last situation here says as the temperature increases, the distribution of kinetic energies of the individual gas particles increases. In other words, notice there's a wider spread from low to high when we increase the temperature. So while we have a few less slower moving particles, if you extend this graph out, you're basically seeing that when we increase the temperature, we've got a wider spread of the particles. So we have particles at more kinetic energies when it's hotter than we have at colder temperatures. And that's actually an important idea that we're going to get into later in the year related to the distribution of energy, is actually related to the concept of entropy, which we'll get into in a later chapter in chemistry. So fundamentally at this point, just know that when it's colder, you have fewer or a narrower spread of different kinetic energies of particles, and your average kinetic energy is going to be lower. But when you increase the temperature, you're going to have a wider spread, so you have more particles at different kinetic energies when it's hotter. Now, section 10.8 gets into the concept of effusion and diffusion. And one, you should understand what they are as a vocab idea. And two, you should understand how they're related to temperatures and velocities of particles. Now, effusion is the escape of a gas molecule through a tiny hole in evacuated space. So this isn't like a tire that you puncture a hole and the particles are coming out because of differences of pressure and they're getting pushed out. It's not really that idea. What we really have is particles bouncing around in this container, and if they hit the spot where there's a hole and there is no hole, then they'll just bounce back and stay in the container. But if we put a small hole in that spot, when those particles strike that position, then particles start to escape. And that's what's known as effusion. Now, the differences in rates of effusion for different gases like helium and nitrogen really is what we're getting at here. How come is it that helium is going to effuse faster? At a particle level, when you look at these balloons, to the naked eye, it looks like, oh, these are perfectly sealed containers. But at a particle level, there's actually gaps and holes in between the rubber molecules that make up the balloon. And what happens is particles escape out those holes through the process of fusion. And it's not that helium molecules are smaller and then get out faster. It's really related to, at the same temperature, what's different between the helium and the nitrogen. Well, the helium is actually moving at a faster speed than the nitrogen is, and therefore it's going to effuse faster. So you would see the helium balloon deflating faster. And that's because the lighter helium has a higher average velocity at the same temperature. And that's actually related to what's called Graham's law. So we're going to come back to this discussion. Why is that true? It's really shown through the concept of Graham's law, which we're going to come back to. Now, diffusion, on the other hand, is not escaping out a small hole. Diffusion is the spreading out of a substance throughout a space. So in the case of spraying perfume, it starts out localized in one spot, and then as the particles of perfume gas disperse, they diffuse throughout the room. And so diffusion and effusion are related but different processes. Now, if air molecules are actually moving at 1,150 miles per hour, doing the calculations of the average speed of particles in a room, that's the average speed of particles. They're moving at a very, very, very high speed. Now remember, they're incredibly tiny, so that's why you don't notice them when they hit you, so to speak, and it's a constant collision that's occurring. But those are really moving fast. How come is it then that it takes time for perfume molecules to spread throughout the room through the process of diffusion? Well, the key is if you look at the picture, you can see why it takes a while. Because when a molecule starts to move, it doesn't get very far before it collides with something else. So air molecules are actually colliding with other gaseous particles in air about every 60 nanometers. That's a billionth of a meter. So it doesn't take very long when it's moving at that high speed before it to run into something and then bounce off. So because of those all those collisions that exist between the air molecules in the room, it takes a while for them to diffuse throughout the room. But it would be true that the faster the particles are moving, the faster they would diffuse. Just like the faster the helium molecules are moving compared to the nitrogen molecules, the faster the balloon would deflate, and therefore the process of effusion was higher. And really what this is called is the mean free path. How far do you move before you collide with something? In the case of an air molecule, it doesn't really move very far. Now, long and short of it, what you really need to get is that smaller particles at the same temperature are going to effuse and diffuse faster. And by smaller, I'm talking about lower molar mass particles. Now, the reason why is really where Graham's law comes in. So why? Well, it goes back to Graham's law, which starts with kinetic energy. If we have two gases in the same room at the same temperature, then they have the same average kinetic energy. So the kinetic energy of gas A equals the kinetic energy of gas B. Now, if you recall when we talked about kinetic energy equation back in chapter 5, the kinetic energy of a particle is 1/2 its mass times its velocity squared. So the 1/2 mass of A velocity of A squared is going to equal the 1/2 mass of B velocity of B squared. So at the same temperature, their average kinetic energies are the same, so their 1/2 mv squareds are the same. Now, multiply both sides by 2, and the 1/2s disappear, and get the masses and velocities on the same side, and I end up with this equation. The velocity squared of A over the velocity squared of B equals the mass of B over the mass of A. Now, get rid of the squares by taking the square root of both sides, and you obtain what's known as Graham's law. The velocity or rate of A over the velocity or rate of B, so the rate of effusion or diffusion of A compared to the rate of effusion or diffusion of B, is going to equal the square root of the inverse of the molar masses. So it's an inverse square root law, is Graham's law. Now, in the past, we actually used to do calculations of Graham's law, but now this is something that's done in first-year chemistry, and AP Chemistry has basically said that they're going to ask you to understand Graham's law from a conceptual point of view and no longer do math with it. So we're not doing this math on the test anymore. So really, you need to understand this law qualitatively, not quantitatively. So except for an extra credit problem in the homework, you're really not going to do calculations of Graham's law. You just need to understand the implications of it. And that was really that at the same temperature, in order for their 1/2 mv squares to be equal, the lighter gas has to be moving at a higher velocity to get to the same energy and the same temperature. So therefore, it's going to effuse and diffuse faster. And that's really what you need to understand at Graham's law. Why is it that the helium balloon deflates more quickly? Because as a smaller particle at the same temperature, it's going to be moving faster, and therefore it's going to effuse and escape faster. And that's what you need to understand about Graham's law. Now, the last section in this chapter gets into real versus ideal gases. And in the real world, the behavior gases only conform to the ideal gas law equation at relatively high temperatures and low pressures. So gases become more ideal, and therefore the mathematical predictions of the ideal gas law and the other gas laws becomes more valid the higher the temperature and the lower the pressure is. So why is it that high temperature and low pressure lead to more ideal behavior of gases, and therefore the opposite? Why is it that lower temperatures and higher pressures lead to gases behaving less ideally and more really? That's what we're looking at in the last section. And then is there a way to account for that in calculations? Now, even the same gas will actually show wildly different behaviors under high pressure at different temperatures. And you can see that in this graph here. The ideal situation is the 1. And at low pressures, we're right at the ideal for all of the gases here. And then, or I should say, for the gas at different temperatures. But as we change the temperature and we increase the pressure, you can say we start to deviate more and more and more from ideal behavior. So under higher pressures, gases behave more like what we call real gases. Well, why is that true? Well, what you need to understand is that some of the assumptions for kinetic molecular theory are assumptions, and they start to break down at high pressures and low temperatures. And the fundamental idea here that we're looking at is a couple of ideas. One, we said each gas molecule has a negligible volume. Well, the larger the actual volumes of the particles are versus the volume of the container, the less of a valid assumption that is. So the bigger the particle and the smaller the volume that particle occupies, we assume it's negligible. Well, in reality, it's not going to be negligible. And under changes in pressure, as we force those particles closer together under high pressure, then it becomes less true that it's negligible volume. And the other issue is really we assume that gases have no attractive or repulsive forces. And under the speeds and distances, that is a relatively good assumption. But not all gas particles have the same intermolecular forces, and this is something we're going to get into more in chapter 13. So we're going to come back to this idea there. But it would be true that particles that have higher attractive forces, intermolecular forces like hydrogen bonding or dipole-dipole, versus London, or large molecules, their London forces become very strong, it's less true that the actual intermolecular forces are negligible as the intermolecular force attractions between particles increase. So these two assumptions start to go out the window under high pressure when we're forcing particles closer together, and under lower temperature when the particles slow down and their attractive forces become more relevant. So that's why it's high pressure and low temperature lead to more real and less ideal gas behavior. So the ideal gas equation can actually be adjusted for individual gases to account for these deviations and make PV equals nRT a better prediction. And what this is really called is the van der Waals equation. Van der Waals was a scientist who was studying intermolecular forces, and one of the things he understood and was able to calculate was how different gases and the different intermolecular forces and volumes of those gases could lead to deviations from the ideal gas law. And this is his equation for basically correcting pressure. Notice this is generally in a P times V equals nRT form, but we're correcting the pressure and we're correcting the volume for gases under specific conditions based upon the gas to make it a more accurate prediction. So the A that you see up here in this equation, so A is right here, that is basically a constant for different gas particles that is based upon the intermolecular forces. So as you look at the different substances down here, as intermolecular forces of the different particles increase, and like I said, we're going to get into why in chapter 13, but as the intermolecular forces increase, the A factor gets larger, and therefore it has a greater effect upon the equation. And then the same thing is true with the B. B is really the volume correction. And you can see as we get larger gas particles, the B factor gets greater, and therefore the correction to the volume becomes larger. So really the van der Waals equation is an equation we can use to convert PV equals nRT into more realistic calculations and take into account the intermolecular forces and the volume corrections of different types of gases. So do you need to know this for the test? No, you need to know conceptually how we deviate from ideal gas behavior and why, under what conditions, and why those conditions lead to deviations. But as far as this calculation, this is just going to be an extra credit in the homework. So this is something you can do one time to improve your homework grade just a little bit. And that ends our discussion over chapter 10.